Go ahead.
Okay.
All right.
So let's welcome Fiona, who will tell us about subsystem symmetry protected topological phases. Please take it away.
Yeah, thanks. So thanks for the invitation. And I'm operating on the understanding that people are going to stop me if there's stuff that they want to know more about or stuff that they don't follow. So please do so. And I'm going to tell you about sort of a cross-section or survey of work done with a few different collaborators. So Trithep, Pranay, Hotat, and Shu Heng. I worked with, when I was on sabbatical at the IAS, Yiji Yu and Trithep, I also worked on a separate set of things before that. And then Oleg Dubinkin and Taylor Hughes at UIUC, I collaborated with on some of the kind of free fermion stuff that I can tell you about. And some of the connections to anomalies were ideas that I first developed with Michael Mulligan some time ago. Okay. So I wanted to start by giving you kind of the condensed matter perspective on, basically on the focus of this talk, which is going to be on anomalies and how they come in and why they're important to the way that we think about things. So basically we, in condensed matter, we're interested in understanding what kinds of matter, can exist and, maybe that you can make in the lab, ideally, although not necessarily restricted to that. And so, the kinds of matter that we understand, we can be very broadly lumped into two types. There are gapped systems, meaning that the Hamiltonian has a spectral gap, okay? And, gapless systems where the Hamiltonian does not have a spectral gap. And so particularly on this side, we do understand a lot about, how to kind of classify different gap phases of matter, especially in low dimensions. So, what are the different kinds of ways to be gapped? Well, one, I think the most exotic way that you could be gapped is you could have what condensed matter physicists call topological order. So field theoretically, that means that, this is a system where in the infrared, it's described by some topological quantum field theory. What that means in practice is that the low energy sort of degrees of freedom, low energy quasi-particles that you see in this system have fractional statistical interactions, okay? So they're not just bosons or fermions. And the poster child for this, which I'm sure at least some of you are familiar with, is the fractional quantum Hall effect, which happens in 2+1 dimensions when you take a kind of gas of electrons and apply a strong magnetic field, and you see the emergence of systems that can be, whose statistics can be effectively described by a Chern-Simons theory, which is, kind of everyone's favorite TQFT, if you will. And where you see these particles in 2+1 dimensions that display braiding statistics that are neither, point particles have statistics that are neither bosonic nor fermionic. So we call them anyons. So it's a very exotic way to be gapped. And in practice, there are relatively few systems that we stumble upon in nature that do this. But there are also a number of less exotic ways to be gapped. And these involve symmetry. So if you don't have topological order, then the only thing that that we have to work with is symmetry. And one way that you can be gapped, but maybe kind of distinct from a trivial phase, is if you have some discrete symmetry which is spontaneously broken. So here's a picture of, and this is, by the way, very common in nature. So here's a picture of the magnetic moments of some atoms in a crystal. And, very often in the crystal, because of the way the orbitals hybridize, these magnetic moments will prefer to line up along certain directions, relative to the crystal axes. And so, maybe these guys want to point either this way or this way along the crystal axis. Okay. And then due to so there's a high temperature phase where there's no long range magnetic order. And here you can see that they have ordered, although in a sort of complicated pattern, where some of them are pointing that way and some of them are pointing this way. Okay. So that's a second way that you could be gapped. And the third way, which is going to be my focus today, which was only appreciated, in the last sort of 15 to 20 years, is you can have what's called a symmetry protected topological phase. So no topological order, no spontaneously broken symmetry where I can look locally and see, oh yeah, there's some kind of magnetic order among these spins and an order parameter that I can measure. These guys in the bulk kind of locally look very boring, and yet it remains the case that they are distinct from what you would really call a boring phase, which is, in condensed matter parlance, we call it a trivial paramagnet. And this is where you have a Hamiltonian whose ground state really can be written as a product state of, separate things on each side, okay? And so a symmetry protected topological phase is something that locally, its physical properties look very similar to this. It's an insulator, okay, it's gapped, kind of nothing, no order can be seen, okay? But in fact, it turns out that there's no way that you could sort of tune the Hamiltonian that leads to this guy here while preserving the symmetry and end up at a Hamiltonian whose ground state is really trivial in the sense of being a product state. Okay. So this is what we know on the gapped side. And what about gapless systems? Well, there are many, kind of very well-studied kinds of gapless systems with a long history. One of the most familiar ones are systems with Fermi surfaces, right? So this is in this plot, these two directions are momentum, okay? And this is an image taken by a scanning probe, and the red lines show where there are, where there's like a density of states at the chemical potential. And this is, I think, copper. And the reason that we call this a surface, it is actually a closed surface because the momentum in a crystal is periodic. So you should think of this, these sides as identified, these sides as identified, and this square is really representing a torus. Okay. So, for example, metals are gapless systems that have typically Fermi surfaces. Another way, which, obviously you can be gapless, is you can spontaneously break a continuous symmetry, in which case you have Goldstone modes. And here you'd have a whole sort of, phase of matter, which is gapless. And I should say also Fermi surfaces are robust. And so, these are also you should think of those as kind of a gapless phase of matter. Now, another reason that you could be gapless is because you sit at a critical point between two gapped phases. So for example, if I look at a phase transition from some trivial paramagnetic phase to some phase with a spontaneously broken discrete symmetry, okay, and some long-ranged order, I have to go through some kind of phase transition or critical point. And if that critical point is second order, there's a gapless, typically conformal field theory describing that. Okay, so these are all various ways that you can be gapless, all of which are very interesting. But the one that I'm going to focus on today is another reason that you could be gapless is that you could be living at the boundary of one of these symmetry-protected topological phases or certain kinds of topologically ordered phases. Okay, and this is where the story of anomalies comes in. So, roughly speaking, nature prefers to be gapped, okay? If you have, a system and you follow the rule that any interactions that are allowed are present, typically, systems will open up a spectral gap around the, say fermionic systems will open up a spectral gap around the Fermi energy. And so it's important anytime you see a gapless system to ask why it's gapless. And as I said, sometimes these can be fine-tuned. So if you're at a critical point, you can have fine-tuning. You can also be protected by, so in the case of Fermi surfaces, we have sort of a counting of degrees of freedom argument that says that's called Luttinger's theorem that ensures that the Fermi surface can't just disappear on you. And in the case where you shrink your Fermi surface, which is the codimension 1 object, down to Fermi, say, points or lower codimension objects, we don't have Luttinger's theorem, but often those sort of Fermi surfaces are protected by a combination of symmetry and topology. Okay. And the third reason is that it could be that you're gapless simply because the symmetry requires that there be a gapless mode, right? So this is the case both for Goldstone modes of spontaneously broken continuous symmetries, as I'm sure you're all familiar with, but also for these boundaries of symmetry protected topological phases. And why does the symmetry require it? Because basically the theory describing this boundary has an anomaly. Okay, and so this is what I want to focus on today is the story of anomalies and their anomaly inflow between the bulk and the boundary as they relate to different kinds of symmetries potentially of interest in condensed matter physics. Okay, and so I think one of the if there's one message that I want you to leave this talk with, it's that anomalies are like, in the past sort of 10 years or so, I think we've really appreciated that anomalies are more fun than, you might have thought, which is to say that there's been a lot of, of course, there's classic anomalies that are very well known, have been known for decades, which, you can sort of see with perturbative quantum field theory. But when you start thinking about these symmetry protected phases, and there's another class of things which are not in my slides, but we can talk about if people are interested, called symmetry enriched topological phases. Okay. But when you start studying these things and, in the gapped bulk, we have certain tools that help us, maybe kind of develop a more complete understanding, which has led also to an understanding of many anomalies that, are not accessible using perturbative quantum field theory. So there's a number of examples. One that I like, that I worked on is sort of, there are anomalies in the way that you can assign symmetry charges to anyons in 2+1 dimensions, such that you can see that certain assignments of charge to these particles with fractional statistics are inconsistent. They have a de Hooft anomaly, and they can only live at the boundary of higher dimensional systems. Okay, and so we've learned a lot about this, and the part of it that I'm going to talk about today is what we've learned about a kind of new class of symmetries called subsystem symmetries, and their anomalies, and the kinds of new sort of gauge theories and symmetry protected phases that come out of this, and finally their relation back to some more laboratory relevant physics, which I think is interesting. Okay, are there questions at this point? Otherwise, I'm going to start kind of getting into more detail.
Actually, I have a quick question. So in this example you gave, can I still understand this 't Hooft anomaly as an obstruction to gauging asymmetry?
Yes, absolutely. Yeah.
Okay, cool.
Yeah. This one is very literally, the way that you see it's an anomaly is you construct, the 2D theory with the symmetry assignments, and you try to gauge it, and you find that that gauge theory is inconsistent.
Okay, thank you so much.
Yeah. Anyone else? Okay, great. So today, I want to sort of turn to this question of subsystem symmetries and other symmetries that are, sort of stronger than what we usually think of with conventional global symmetries. So I'm going to introduce this subsystem symmetry in a minute, but let me start with an example that I think is a little bit, more relatable, which is, so we all, like to think about systems which have U1 charge conservation. We have tons of those in nature, right? Certainly in condensed matter, our typical system has a U1 symmetry. And we know a lot about what that does. But something that is relatively unexplored is, suppose that not only the charge is conserved, but also some number of higher multiple moments are conserved. And so the minimum thing that you could think of is a system that conserves both the total charge and also the dipole moment. Okay. And, this is so this is, it's not that we're introducing a new symmetry group when we talk about dipole moment conservation, but it is a much stronger symmetry, which gives rise to sort of different classes of behaviors than thinking about U1 charge conservation alone. And so I think, kind of physically, the thing that maybe is most plausible in terms of realizing is something like dipole moment conservation. But I'm going to start by talking about something we call subsystem symmetry, which is, if you like, a stronger version of dipole moment conservation in which not only is the dipole moment conserved, but the dipoles are sort of restricted in their mobility to only move perpendicular to their dipole moment. Okay, and so in both of these cases, it turns out that you can sort of characterize the difference between, sorry, not characterize, you can understand why the kinds of, theories that you could get, and in particular, the kinds of anomalies that you could get with these symmetries are different from what you would get with ordinary global symmetries. You can think of that as resulting from the fact that if you sort of couple these dipolar objects to gauge fields, that those gauge fields naturally are different from the gauge fields that couple to the charge. And in particular, they transform not in a vector representation of spatial rotations, but in a tensor representation, okay? And so these, and whereas there's sort of, one vector rotation, and even if I work on a lattice where the rotational symmetry is discrete, typically the vector rotation, representation is in the continuum limit is relativistic. These tensor representations are often not. And so we end up with theories that have a much more interesting and much more intimate knowledge of the lattice rotation, subgroup that was built into the model. And so these are not theories that you would write down if you're looking for something that's relativistically invariant. Okay. And so you might ask, why would we expect, so why would we expect that we're going to get something new with dipole conservation? And one of the first hints that there was something there came from a very different avenue than trying to write down sort of quantum field theories or topological response theories, which was just through the study of band theory. And so the concept was dubbed higher order topological insulators, and it was introduced by Benalcazar, Bernavig, and Hughes. And the basic idea is that, if you have a filled band and its total dipole moment is 0, its quadrupole moment can be quantized. Okay, again, if you have some crystalline symmetries such as reflections or rotations, and they showed that under these conditions, new kinds of sort of topological invariants of the band structure exist. And so you should think of the symmetry that lives in this band as a global U1 conservation with an effective dipole moment conservation, which is not a microscopic symmetry, but is a symmetry of the filled band, as well as, you typically need other symmetries like time reversal, rotation, reflection. And so they sort of introduced this concept, they laid out the band topology, and they showed that this leads to new kinds of gapless modes, that are different from what we knew before. And so what this picture is showing is the following. So on the left here, we have a picture, a kind of schematic of a three-dimensional topological insulator. So that's a conventional symmetry-protected topological phase. The gray in the bulk indicates that the bulk is gapped and, looks pretty boring. And then this kind of orange and yellow shiny surface indicates that everywhere on the boundary of this system, you have these gapless modes, which are sort of protected by the fact that there's an anomaly inflow between the bulk and the boundary. And so, anytime you have this symmetry protected bulk, as long as you don't break the symmetry, you must have these gapless boundaries. Okay. And then, so this is the case if you have, for example, time reversal and global U1. If you now instead have time reversal, some appropriate lattice symmetries, and sort of band with an effective dipole conservation. Okay, so dipole moment 0 in the band, which is a definite value. Then you can have this quantized quadrupole moment, and that has some topology associated with it. And what you find there are these gapless modes not along the surfaces, but if you connect two surfaces together, you get these gapless, what are called hinge modes. And then finally, so they made the point that you can kind of keep going. And so if the net quadrupole moment is 0, you can have quantized octupole moments. And then in 3 dimensions, you get for example, gapless modes at the corners of the cube. Okay. And so this was sort of a hint using very different approaches than what I'll show today, that there's something with new, okay, some new kind of topology that occurs in systems with a sort of dipole moment conservation. And so, and I should say, in condensed matter, ultimately, I think some of the most interesting questions, are to do with what we can realize experimentally. And one of the great things about band theory is that when, it's relatively easy to tell experimentalists where to look. And so this, higher order topological insulators has been very fruitful, kind of experimental endeavor over the past few years. And so there's good reasons for wanting to kind of understand these systems very well. And you might ask questions like, okay, well, we do understand in the case of topological insulators what there's anomaly inflow between the bulk and the boundary, and that's been well fleshed out. What kind of anomaly inflow is there here, and how should we think about it? And if you understood the anomaly inflow, you might be able to do something like passing from, say, topological band insulators to our full kind of universe of symmetry protected topological phases, where we could write down, kind of by understanding a full classification of these kinds of anomalies, we could understand, a much larger range of phases than are accessible through band theory, which is really a theory of non-interacting electrons, and understand, more broadly what kinds of phases of this type we could get. Okay.
So a question.
Yeah.
On the previous slide, in the bulk, you have a non-relativistic invariant system.
Yes.
But now on the edges and the hinges, can it be relativistic invariance, or must it be non-relativistic?
Yeah, it can. Yeah, it can be. So the kind of canonical example here would be that you would have sort of counter-propagating, chiral, if it's a fermionic system, counter-propagating chiral fermions. Yeah. So I mean, yeah, that's right. So I think it'll be a little easier to talk about this when I kind of write down some gauge fields. But when you look at the topology, the response theories for, the effective gauge theories that describe this, what you'll see is that, in the bulk, because of the conservation laws, it's tempting to write down, or you end up writing down things that are really, not relativistic and know something about the lattice geometry and symmetry. But when you dimensionally reduce those theories to the boundary, sometimes, these tensor things can reduce to vector things on the boundary, basically. And there's some additional nuance, which is that, when we talk about subsystem symmetry, we really are dealing with tensor gauge fields. In some of the effective response theories for these dipolar systems, it's a little different than that. It's not really a tensor gauge field. It's that, the thing couples to a derivative of the electromagnetic field, which, sort of looks like, or, transforms like a tensor gauge field. And so there's this, there's a little bit more nuance there to that as well, the way that these boundary terms drop out.
These gapless systems, for these gapless systems, can they be non-relativistic as well?
Do I know of an example? Yeah, I will. Yes, I will show you an example actually at the end where we have a two-dimensional system which has gapless modes, which are very definitely not relativistic. Yeah, that one comes out of a subsystem symmetric bulk. Yeah. Yeah, so it can go either way. These ones happen to be. Let me put it this way. The ones that I know how to get out of, an actual sort of band insulator, so like band topology type picture, where the bulk is fully gapped. In those cases, it does seem like these boundaries are relativistic in the examples that I know. But I don't know of a fundamental reason for that. Yeah. Yeah. Okay. Okay, so, you might think that the interesting thing is to kind of to understand, these examples that we can access in the lab. But to get there, I'm going to tell you about some anomalies and theories with this stronger kind of symmetry, subsystem symmetry. And that's basically because in that context, I think it's fair to say we have a better understanding of the field theories and better kind of control of what we write down. And then I'll show you some, connections back to band theory, which I think are interesting. Okay. And so in order to do that, I got to talk a little bit more about what is subsystem symmetry. And so subsystem symmetry, unlike dipole conservation, where you just go from global charge to the next multipole moment, subsystem symmetry, you should really think of as making the symmetry group much larger. And so maybe for some people in this audience, it's better for me to say that it's sort of like it's sort of like a one-form symmetry in which you've sort of fixed the positions of the lines along which the symmetry is going to act. Okay. And so rather than having, so a U1 symmetry on this 2D system would tell me that the charge of my whole 2D system is conserved. If I have a subsystem symmetry, instead of that, I have a conservation law that acts separately along some set of subsystems. And the kinds of subsystems that we're going to look at today have the feature that, if I work on the square, that they're sort of intersecting. So if I work on the square lattice, I'm going to have a conservation law of charges along these vertical lines and also a conservation law for charges along these horizontal lines. And, you can write down models that have a wide variety of subsystems. I'm going to talk about, fairly straightforward ones like lines in 2D or planes in 3D, but you can also, write down things with sort of fractal subsystems, and those are a slightly different beast, but also very interesting. Okay, so when I have this conservation law, what does it mean? Well, the first, very obvious thing is it very strongly restricts what the particles in my system can do. So if I have this conservation law, then individual charges are not mobile. So if I take a charge here and I try to move it over here, that's going to violate the conservation law on this line, right? If I try to move it up or down, it's going to violate the conservation law on this line. And so the charges are immobile. However, if I make a dipole, right? So red is supposed to be a particle and blue is the antiparticle, okay? If I make a dipole, then these guys can move, and you can check that as long as they move perpendicular to their dipole moment, all of the conservation laws, all of these, U1 symmetries and the corresponding conservation law along each line are respected. Okay. And so in order to sort of understand these symmetries better, it's nice to understand what kinds of what gauge fields couple to them. So anytime we have a conservation law, we can think of a conserved current, and we could imagine coupling that conserved current to a gauge field. And it's not too hard to convince yourself that in this case, the right kind of gauge field for the particular example that I wrote down, okay, so these lines on the squared lattice, is a tensor gauge field. And so why is that? So I'm going to call my tensor gauge field. So sorry, this field has two components. It's got an A naught, which is going to live on the sites of my lattice. Okay. And A naught under gauge transformations goes to A naught plus DT alpha. Okay. And then it's going to have a second component, which I'm going to call AXY. And I'm going to put that at the center of a plaquette. And the reason I do that is because under gauge transformations, AXY transforms to AXY plus DX dy alpha. So it's got this second derivative of the gauge parameter. Now, why would you say this is the right, way to couple a gauge field to something with subsystem symmetry? Well, the reason is that these gauge transformations are associated with a current conservation law, okay? And the current conservation law associated with this particular set of gauge transformations is this one here. So if rho is the charge density, right, rho is J0, then dt rho is dx dy of jxy, okay? And so now, if you imagine putting periodic boundary conditions in the x and the y directions, right, and you integrate this, both sides of this equation around, say, a closed curve in x, as long as jxy is single valued, I'm going to get 0 on the right-hand side, and that's going to tell me that along, say, any line in the x direction, the change of the charge in time has to be 0. In other words, the charge is conserved. And so this conservation law, sorry, this conservation law implies that the charge is conserved not only globally, but also along all of these lines in x, each line in the x direction and each line in the y direction. Okay, good. Okay. And so, similarly, I could write down some more complicated set of subsystems, but, for each set of subsystems, there's a natural choice for a gauge field such that you get the right conservation law. And that is why, so these, subsystems naturally lead to gauge fields because they have stronger conservation laws. They naturally lead to gauge fields in these tensor representations rather than vector gauge fields. Okay. All right, good. So that's the that's subsystem symmetry and how we gauge it. And so now I want to, sort of just give you some examples. So now we'd like to understand, what can we do without breaking subsystem symmetry that could lead to different phases of matter. In other words, can we find symmetry protected topological phases for these subsystem symmetries? And in order to do that, we want to look for analogs using these tensor gauge fields of familiar anomalies from quantum field theory. Okay. And then we want to know, so given an anomaly, you want to know, is it something that lives at the boundary of a symmetry protected topological phase in higher dimensions? And so to do that, we want to understand, what are the kind of response theories that we can write down for the bulk that would exhibit anomaly inflow between the bulk and the boundary. Okay. And so what I thought I'd do is just, kind of give a few examples of things that we know how to write down. I would say that our understanding of these terms is not exhaustive, but interestingly, the examples that I give are kind of analogs in many ways of things that are very familiar from relativistic quantum field theory, which maybe kind of gives you some indication that the anomalies here are not that different. So let me give you the simplest example of a sort of bulk topological term, which we can associate with a gapless boundary mode. And that would be the topological theta term in 1+1 or 3+1 dimensions. Okay. And I should say that all the theories that I'm writing down are just response theories. So when I write these gauge fields, you should think of them as non-dynamical. This is just a theory that's sort of telling me how my system responds to a static background, classical background field. Okay. And so these theta terms are familiar in condensed matter physics because they describe, topological insulators in 1 and 3 dimensions whose boundaries have gapless fermions. And so how does this work? So in 1 dimension, the theta term just looks like I have a theta over 2 pi times the electric field. Okay. And if I also have time reversal symmetry, so, theta is periodic modulo 2 pi. And if I also have time reversal symmetry, then there's only 2 values of theta that are compatible with time reversal symmetry, because time reversal is going to take theta to minus theta. One such value is 0, but the other value is pi. And so these are, 2 distinct theories. And because theta is quantized due to the time reversal symmetry, we might think that there's some kind of rigidity and that these represent distinct phases of matter. And indeed, that turns out to be the case. So let's talk about this one-dimensional theta term and what it tells us about a phase of matter. So this is a total derivative in the bulk, but if you like what it tells you, okay, is that the charge density, okay, which is if you take the equations, if you coupled this to some, current, and you take the equations of motion, what this theory tells you is that there's a charge density at the boundary of the system where theta changes from between 0 and pi, okay? And so if I took a boundary between, theta is 0 and theta is 0, the boundary charge has to be integer. But if I take a boundary between theta is 0 and theta is pi, then I get a boundary charge that's a half integer. And this tells me, this half integer, sort of charge tells me something non-trivial is happening. And there's a famous sort of model that gives a very simple picture of what's going on called the Schrieffer-Heeger model, and for a one-dimensional topological insulator. And basically the idea is that, here I have 2 sites per unit cell, which is why we've kind of drawn these zigzag things. And if I have an integer number of unit cells and I'm at sort of half charge filling, then there's 2 different things that I could do. So I could have the 2 unit cells, the 2 sites in the same unit cell be strongly coupled. And then, I have sort of 1 charge per unit cell for sure. And then the other thing I could do is have a strong coupling between, 1 site in the unit cell and a site in the next unit cell. And in that case, we see that there's these 2 sites at the end of the chain that are sort of decoupled from the rest. And they collectively have to hold, one charge. And so this is where this comes from. Okay. And so that's a 1D theta term. And so what's the analog of that for these higher rank gauge theories? And indeed, it turns out to be sort of the obvious thing. So for the set of gauge fields that I wrote down a couple of slides ago, this A0 and AXY, there is an electric field term, right? Which looks like, so it's a gauge invariant, combination of derivatives of A0 and AXY. And it looks like this, dxdy A0 minus dt AXY, okay? And so we can write down a topological term in the action, which just looks like theta E. And again, you can show that for these higher rank gauge fields under appropriate, assumptions about their compactness and therefore the kinds of large gauge transformations you can have, that theta is again periodic modulo 2 pi, and therefore we have these 2 values of theta compatible with time reversal, okay, 0 and pi. And again, what this theory is telling me is that there's a charge density. Okay, this, if I add this theta term to my system, what it does is nothing in the bulk, but it modifies the charge density along the boundaries, and it modifies it in a specific way. So here, these second derivatives are sort of important. And so what I see is that, so there's going to be a sort of a bulk term, which is dx dy theta, okay? And then I get a dx theta term along these boundaries here, right? And a dy theta term along these boundaries here. And then we get a sort of a term that's theta by itself evaluated at these corners. So what does this mean? And so you can kind of break this down. So if I have a dx theta term along this, say, top edge at y is y0, then this corresponds to something describing some kind of polarization along the top edge. Okay, which is to say that if there's some polarization when I look in the middle, I don't expect, so this polarization, I think maybe the field theoretic way to say this is that this kind of looks like what you could write down for a one-dimensional topological insulator along the edge. So, if theta is uniform along this edge, but jumps to 0 at the end, then what you would have is exactly a one-dimensional topological insulator along the top, right? So I have these top terms, and similarly for the side, I have a theory that looks like a one-dimensional topological insulator along the side. Okay, so these, so these are just sort of 2 one-dimensional systems, and that doesn't seem like anything too exotic, but there's this other piece, right? Which is this value at the corner. And so what you find is that what this theory is telling you, and then, okay, so this is the bulk piece, and then we've, this is what we get by integrating by parts. So this piece actually doesn't contribute, okay? But so what we find by looking at this is that we have this theory that says, we could look at the top edge. So we can look at the top edge and ask, does the top edge look like it's a trivial or non-trivial topological insulator? And then we look at the side edge and ask, does the side edge look like it's a trivial or non-trivial topological insulator, right? And if one of these was a yes and one of these was a no, we would expect to find a half charge at the corner. But then there's this extra corner term, which tells us we get exactly kind of the opposite thing that we think, right? And so there's this switching of what you see at the corner relative to what you would expect from the sides, and that's sort of the hallmark of this higher rank theta term. Okay.
Can I
so
ask
this
a question?
Yeah.
Sorry, we have a feedback.
Yeah, I'm trying to.
Can you just
I'm sorry.
let's try to fix this, and I'll ask it later. Thank you.
Do you have two devices on?
Yes.
Okay, that's probably why. If you have two devices on, if you do you want to try asking, or
We can try now. We'll try to mute the
yeah, if you like turn off the audio on one of your devices
later, because we are in a room which doesn't have a mic. Oh, here we go. Yes. So I didn't understand fully. How do you, because you have theta in the bulk, theta equal pi, and outside is theta equal 0.
Mm-hmm.
But you're still assuming some kind of a smooth transition. What do you have in mind, or is it a abrupt transition?
Yeah, no, here, yeah. So here I'm assuming a drop transition. Indeed, a sudden transition. So these are. So the fact that I'm evaluating this only at y is equal to y naught means that I'm assuming that dy theta is 0 everywhere except at y equals y naught, right? Otherwise, I would have some region. So it could be smooth, and then I'd have some region near the boundary where theta is changing. And then I would have to, kind of. So as long as that region is kind of exponentially localized near the boundary, I don't think it makes much difference. But and then the statement would be that you kind of have this theory of a one-dimensional topological insulator, but it's a little bit thick. But the reason, but let me say one thing. So the reason that we want theta to drop discontinuously like this is that if we have this smooth transition, then theta has to go through some values that are not 0 or pi. And the time reversal symmetry is actually important in these things. So the kind of the fact that I have two, so the fact that I have two states here has to do with, I'll write down a model, okay? And the model, is a spin 1/2 model. And the fact that you have a degeneracy of states has to do with the fact that, on this particle, it's a t squared is equal to -1 particle. And so the fact that you have this guy by itself means that you have to have a degeneracy. And that's what we mean by a gapless state in 0 dimensions, which is maybe not obvious. Does that help?
It helps, but that's what confused me, that you are assuming that some derivatives are non-zero. But if theta is either 0 or pi, then these derivatives should also be, or should I think of them as discrete differences, and this derivative is really 0 or pi or a multiple of pi?
Yeah, that's right. So I think the way that implicitly the UV regularization that we use in condensed matter is a lattice, right? So, I have a crystal and theta is pi all the way to the end of the crystal. And then, maybe I have a different crystal out here and theta is 0 in this crystal. And of course, in real life, when you grow interfaces, it's never that simple. But, as a theorist, at least I can I could write that down, right? And so indeed, but yeah, so in principle, yeah, so I misspoke earlier, right? In principle, I could imagine a smooth transition of theta, but the problem with that is that when theta is changing smoothly, time reversal is broken. And then once time reversal is broken, you don't necessarily see this degeneracy at the ends.
I see. Thank you.
Yeah, cool. Okay. So good. Okay. So
Sorry, I have a
yeah, so
small
right.
question.
So this is sort of the thing that, if I don't add, I could
There's
come along with a
question,
1D.
actually.
Yeah. Yeah.
Okay.
Go
May I
ahead.
ask the question?
Yeah.
What happens if I consider not a square but a disk?
Right. Yeah. So that's an interesting thing that in these systems, okay. So if I kind of naively take this field theory, right, and I put it on a disk, you would be like, oh, weird. There's no corner modes, right? But I think it's also fair to say that the choice of, and in open boundary conditions, I can do that, right? There's nothing wrong with putting it on a disk, but you might say, why is the square the natural thing to look at? And the reason is that when I choose these subsystem symmetries, like at some level, I'm choosing a lattice. And so if I drew a disk, I'd have to I think the easy way to see what's going on is you should really be putting a lattice in your disk, right? And then you're going to have a whole bunch of step edges there. And actually, off the top of my head, I'm not quite sure what happens when you have sort of a, but you're going to have to put these sort of, if you really figure out where all the subsystems are, it seems like you're going to have to put these corners somewhere. And so, but yeah, I haven't thought about in detail, like what that looks like, but I would say the choice of subsystem gives you kind of a preferred choice of boundary, the simplest boundary, which is this one.
Okay.
But yeah, it's indeed, it's not the same. Does that satisfy you?
Yes, partially. Yeah, thank you.
Partially, yeah. Yeah, I agree. It's a yeah. I wish I could tell you off the top of my head exactly, what happens. But naively nothing happens because we don't have these dx dys. But yeah, I think it's a little more complicated.
Thank you.
Right.
Can I
Yeah.
ask a quick question? So
Yeah.
does this mean that the phase changes if you stack kind of a lower dimensional SPT on the boundary?
Oh, perfect. Yeah, this is a great question. So the question is, so, when we talk about classifying bulk phases of matter, there's this paradigm that we use in condensed matter, which is, it's okay for me to say the boundary effect is telling me something interesting about the bulk if I can't get rid of that boundary by just adding some lower dimensional system to it, okay? And the underlying reason for that is that if there's an anomaly floating around in the bulk that the boundary is canceling, then that means that boundary theory does not exist in lower dimensions. And so here it's a little bit subtle, right? So I could say, the fact that I have this sort of half charge or degeneracy on the corner, that part I can get rid of by adding a 1D topological insulator to the top, right? So, when in the field theory that I wrote down, this top part looks like a 1D TI and this side part looks like a 1D TI. And then we have this extra corner. And so that's sort of, 3 halves, if you will, which is the same as 1/2 because, these half charges are well-defined modulo 1, okay? And now I could come along and I could say, well, I'm just going to glue one of these sushi for Heeger chains to the top boundary. And then that would give me, instead of 3 halves, 4 halves. and I wouldn't see this gapless corner mode. But you can still tell that there's something wrong with this system, because I would say, well, on the top, if I measure the polarization up here, that polarization is going to look like a phase with theta is 2 pi in the bulk, in my 1D bulk, right? And so that would be like a trivial insulator. On the side, I'm still going to have my 1D topological insulator, but at the corner, I get nothing. And so the, so the anomaly is, manifesting itself in the mismatch between these the polarizations on the edges and what we actually see at the corner. And that's sort of what's going on here. Does that make sense?
Yeah, thank you.
Cool. Yeah. Yeah. And and again, this sort of half charge, what's sort of special about it is that we get this degeneracy, a t squared is -1. And so, yeah, so let me sort of show you just a schematic of, the analog of a Su-Schrieffer-Heeger chain. So let's imagine that, so each of the pink squares here I'm going to imagine that I have a site in my lattice. And on each site, I have, 4 spin-1/2 degrees of freedom, okay? And then, roughly speaking, how would I get a phase like this with subsystem symmetry? Well, the first thing is that, kind of in the book, in order to have subsystem symmetry, I have to have 4 particles interact together, okay? And so I'm going to take, one way I can do that is just to take, 4 spins, one from each of the 4 sites surrounding the plaquette, and kind of bind them together into a singlet state in a specific way, okay? So I have to make sure that this is unique. And then that leaves a whole bunch of stuff along the edges. And in the edges, I can, compatible with subsystem symmetry, I can basically just get rid of these 2 spins here. I can couple them up into a singlet. But because I've got 3 spins on the corner, I sort of have a leftover spin 1/2. And this has a Kramer's degeneracy due to the fact that t squared is -1. And so that's my kind of, half charge in the system that leads to what we would call a gapless corner mode. Okay. So that's the simplest example. And, so here I should say you can write down this theory for the higher rank gauge field AXY, and then you can, you can see that this field theory here, if I wanted to describe, maybe an ordinary higher order topological band insulator that doesn't have subsystem symmetry, then AXY, then I need to replace AXY with some combination of the vector, something involving the vector gauge fields. And under gauge transformations, the thing that you would naturally write here is not AXY, but dxay plus dyax, so a symmetric combination of derivatives. And that would give you a response theory that sort of captures these corner charges, which are seen in the topological band theories. Okay, so that's one example. I'm actually going much slower than I thought. So another example. So let me try and go through this a little more quickly, and then because I don't want to keep people way longer. So another classic anomaly that we think about is the axial anomaly in 1+1 dimensions, right? And so as you all know, the axial anomaly is something that happens when we have two. You can write down here's an action. Okay, we can think of this as a bosonized action for fermions. And it has 2 conserved densities. One is the U1 charge, which we can think of as the number of right movers, guys over here, plus the number of left movers. And the other one is this axial current, which, so here I've drawn a more condensed matter version of this, where this is energy versus momentum, and my right movers live at momentum plus kf, and my left movers live at momentum minus kf, okay? And so in condensed matter, the axial current is naturally kind of becomes a momentum current, okay, or momentum density, which depends on the difference of these, okay? And then that, okay, so the electromagnetic current in terms of these bosonic fields, the electromagnetic charge density is dx phi. This is something that if you open up a bosonization textbook, you'll see this, right? And so then the Jx is then dt phi, and this current is just conserved by equality of mixed partial derivatives. The axial current is a current that's conserved when you actually basically flip these two, okay? So now the density is dt phi, the charge density, the current density is dx phi, and this is conserved due to the equations of motion. And so when I turn on a background electric field, that modifies the equations of motion, and the axial current is no longer conserved, right? And we know what's happening in our condensed matter system. When I turn on the electric field, I'm basically changing the potential at these, plus kf relative to minus kf. And so some of these, these electrons are sort of moving over through this Fermi sea and getting pulled down from the left movers are getting pulled down here and pushed up out here on the other side of the Fermi sea as right movers. Okay. And so the interpretation of this in condensed matter, 1D metal, is just that, when I apply an electric field to a material, the momentum is not conserved. Momentum is not a conserved current. So we have an analog of this anomaly as well for higher rank gauge fields. And so let me start with an action that looks like this. So instead of dt phi squared minus dx phi all squared, I'm just going to stick an extra dy in here and work with this action. Now note that this is an action for a free boson, okay? But it has a very unusual dispersion, okay? Which is to say that the omega squared, so the energy is 0 anytime kx is 0 or ky is 0. And you can also see that this has a subsystem symmetry, because if I shift phi by any function of x plus any function of y, this action, this Lagrangian is left invariant. Okay. And I should say this will so come back, but this theory is pretty weird. So, you have to be sort of careful if you think about regularizing these theories, because the energy cutoff, imposing an energy cutoff is very different from imposing a momentum cutoff, right? These lines, the zero energy lines, in principle extend out forever if you're writing a continuum field theory. And so that introduces some subtleties in the regularization. Okay. But so, much like the 1D axial anomaly, this theory has two conserved currents. It has one where, we have this kind of, if you like, you could literally think of this as a dipole density. If you took dx phi to be a charge density, then this is the, the dipoles of that charge. And this one again is conserved by equality of mixed partials. And then there's another current, okay, where again, I basically just flip the roles of J0 and JXY, okay? And this is conserved, again, only due to the equations of motion. And so once again, if I couple this to a background sort of gauge field of my first, I couple my first to my first conserved current in this way, and I apply a background field that modifies the equations of motion, and I see that this second current is no longer conserved. So I get something like an axial anomaly in this subsystem symmetric system. And so what's going on here is we can think of this really, as something very similar to the axial anomaly, but in a system of dipoles. And so with my subsystem symmetry, if I put the dipole moment in the y direction, then my dipoles can be either, they're constrained to move along x, right? So I can really think of them as left moving or right moving. And so I can think of this as, the 1D axial anomaly in the x direction for dipoles whose dipole moment are in y. But it turns out that actually that's the same thing if you look at the way the actual charges move, as saying, well, these dipoles, I'm looking at guys with dipole moment in x, okay? And then, it's an anomaly for things with dipole moment in x that are, left or right moving in the y direction. Okay, so these are two equivalent pictures in the subsystem symmetric language. And, once again, what's happening when I apply this background higher rank electric field is that I'm sort of tilting the zero of energy at the left and right branching momentum space, if you will, if I wrote a kind of 1D model. And so I'm causing left movers to turn into right movers. Okay. So this is the analog of the 1D axial anomaly, and you can ask, is this is this an anomaly that tells us about a higher rank symmetry protected topological phase of matter? And indeed it does. Okay, so you can. So, a 1D chiral anomaly can be canceled by a bulk Chern-Simons term. In this, axial anomaly can be canceled by a mutual Chern-Simons theory in the bulk. And this is essentially true also in the higher rank case. So if I introduce two higher rank gauge fields, I'm calling them A and B here, and I couple them together with this kind of mutual Chern-Simons theory, they can cancel this boundary anomaly. Okay. Now, I should say something about, or I want to emphasize something about this Lagrangian here, which is that so on the surface, I have introduced this anomaly by saying I have subsystem symmetry, separately along these X and Y lines. And there's more than one way that I could think about continuing that into the bulk. The minimal thing I could do is to say that I have this, if this is kind of the Z direction going into the bulk, that I have subsystem symmetry along XZ planes and YZ planes. Now, I could also try to introduce subsystem symmetry along the XY planes, but it turns out that that's not the that doesn't seem to yield a theory that can cancel this anomaly, at least not one that we were able to write down. And so this extension here is the most natural one to think about in terms of canceling these boundary anomalies generally. Okay. And that's why I have a BZ and an AXY and an AZ, BZ, BXY, AZ, AXY. Okay.
When you start with this bulk theory, is it clear that this is sort of a unique boundary condition, or do you have other choices of boundary conditions of theories that actually have the same anomaly will be canceled by this?
Right. So if I understand your question correctly, you're saying like you can ask, can I add, sort of local terms to this action at the boundary that would modify the anomaly?
No, I'm asking sort of if you have this bulk theory, and it's basically anomaly theory for this particular boundary theory. But if you just take this anomaly theory, could you impose other boundary conditions on the fields that would lead to, say, other theories than the one that you have on this gray surface?
On the boundary.
So like different boundary conditions on this bulk Chern-Simons theory.
So
what would be sort of the class of theories that you would get?
Right. Okay. So one way in which the boundary conditions are certainly important is if I one thing is this is a sort of classical response theory. So, we're not like, there's certainly a lot of stuff that could happen if these guys were dynamical that we're not looking at. But one thing that I could certainly do is I could, impose some boundary condition that effectively breaks the subsystem symmetry. And that would certainly be different. Whether there are other.
So I'm asking something much more basic. Like, for example, if you had a Dicraft-Witten theory in the bulk, there are different types of sort of boundary conditions you can impose on it to get, say, you know, electric, magnetic, dual versions of the theory on the boundary. So if you had lines and that
Right.
propagate in the bulk, then they could actually end, or they could become joint.
Right.
So I'm asking,
Yeah, okay.
when you have that kind of mutual transaminance theory, when you put this sort of, like if you put it on a slab and you have this boundary, can you characterize
Right.
what kind of theories are actually share this bulk theory as an anomaly theory?
Yeah, okay, so, and you have in mind like these, yeah, okay.
These symmetries.
Right, so I don't know, that's an interesting question, and off the top of my head, I don't know the answer.
It would be interesting to see whether you would get, say, very specific theories that where you could gauge the subsystem symmetry, or anyway.
Yeah, no, I would love to talk more about this after the seminar,
sure.
if you want to, because yeah, in this context, I haven't thought about this, but I hear where you're coming from, and I would have to think about, yeah, whether whether I have anything to say. Yeah. Okay, but yeah, so let me just kind of say that, you know, this, so this bulk, you know, certainly if you ask, you know, what happens to this bulk under local gauge transformations, you find that, like, you know, as is always the case with these mutual transaminance terms, that it's only gauge invariant up to a boundary term. And then you can show that that boundary term actually, you know, cancels the anomaly at the boundary. And so this is the kind of anomaly inflow mechanism. And okay, so let me, okay, I'm going to say one more thing, and then I'm going to, you know, I might sort of skip to the end, or, you know, check in with you guys on time. So you might ask, so this is, you know, some kind of theory, and it has a bulk, you know, a bulk response theory and a boundary, and this is anomaly inflow. So it kind of looks like it fits the criterion for what we would want to call a subsystem SPT. And you know, it has these protected surface states that have to be there to cancel the anomaly. But to really convince ourselves that we should call this like a subsystem SPT, it's interesting to ask the question, can we also get rid of this surface anomaly just by stacking, you know, some lower dimensional systems, right? So, you know, maybe I have some system with the same symmetry, but these are just some kind of two-dimensional SPT phases, you know, rather than really these kind of coupled three-dimensional things. And so the answer is you can show for this particular field theory that that's not the case. So this is really describing something that's, you know, intrinsically subsystem symmetry protected. And this, you know, builds off some work by my collaborator Trithep Devakul, as well as Dominic Williamson and Juven Wang. And they sort of show that if you take two-dimensional theories and you characterize, so these boundary anomalies are characterized by something called group cohomology. I won't go into the details, but if you characterize, so you can sort of so basically group cohomology is about which symmetry generators fail to commute with each other in these systems. And you can actually show that you can sort of characterize the pattern of these, you know, sort of non-trivial group cohomology elements along the edge, okay? And for these strong SSPT things, what you can see is that they have a sort of chaining pattern, so you can't just get rid of them by stacking up clusters of lower dimensional things. And we can show that this field theory in terms of these higher rank gauge fields, if you sort of put it on a lattice and ask which kind of SPT, you know, which class it lives in these sort of chained classes. And so these are indeed sort of strong, truly subsystem protected systems. Okay, so let me check in with you guys on time. So I do have a couple of things to say about, you know, bringing this rather esoteric kind of symmetry back to something that connects to band theory, but I can also just skip to the end if people want, you know, you let me know.
Maybe a couple of more minutes, 5-10 minutes.
Okay,
maybe.
yeah, sure. So let me try to go quickly. So Yeah, so one of my, favorite things about this is that it all seems really abstract, but in fact, if you look at, so I'm going to focus on this, kind of higher rank axial like anomaly. And you can ask, does this anomaly tell us anything about like maybe a system? So, I showed you how these corner things connect up to higher order topological insulators. This axial anomaly, does it connect to anything that we might plausibly talk about in a real system? And the answer is yes. And one way to see this is, so you could say, let's just write down a model for fermions, which has these lines, these funny lines of zero modes. Okay, so this is a picture, this direction is energy, right? And these are two momenta, it's a two-dimensional system. And so there's a picture of the fermion energies and they have this kind of saddle point, okay? Looks like this. And because these are free fermions, this model has the following conserved quantities, so the total charge. And now it has actually two conserved momentum, the momentum in the x direction and the momentum in the y direction. Okay. And okay, that looks kind of different from this conservation law that we had, but if we sort of impose some kind of reflection symmetry on this system, we could sort of think of these two as related by reflection, and then we would have a single, conserved quantity. That's not too important. So now you can ask, so imagine that I had a fermionic system that looked like this, and I applied an electric field in, in this y direction, okay? And so on this side of momentum 0 at positive kx, I have fermions that are right moving in y, right? So this is kind of going from positive energy to negative energy. And on this side of the Fermi surface, I have things that are left moving in y. And so what I see when I apply an electric field in the y direction, the total number of left movers and right movers is the same. So that's not a problem. But I see that I get basically a creation of particles over at plus kx and loss of particles over here. And so what I get is lack of conservation of this momentum current. Okay, so you can think of this momentum current non-conservation as a sort of manifestation of something that's very similar to this axial anomaly that we see in 1D, sorry, in 2D subsystem symmetric theories. And so now you can ask, now what is different in these fermionic theories is you can ask, what I have this anomaly, okay, and so if I'm going to have translation symmetry, this sort of can't live as a two-dimensional system on its own. That's obvious for condensed matter people because you're drawing a Fermi surface that's not closed if you only have a single point of this type. Where can you put it? And the answer is you can actually put it on a specific type of three-dimensional semi-metal called a Weyl semi-metal. And so what's special about the Weyl semi-metal is I can actually have a Fermi line that ends, and it ends on these gapless points in momentum space in the bulk. And if I have my Weyl nodes and arrange them in a kind of quadrupolar pattern, then I actually see this anomalous surface state. And so, okay, so there's a topological response. Let me maybe skip that. This is just, to say that to describe this Weyl semi-metal and its momentum energy response, we write down something that, you can think of as very much inspired by this response theory that we write down in the subsystem symmetric system, which is bulk, which is however, describing in that case a gapped bulk. But why would the bulk action be similar? It's because you're sort of canceling the same anomaly. And so let me kind of just end there, but maybe the big picture here is that so anomalies are really, really important in condensed matter physics. They tell us about something very physical, which is when we get interesting gapless surface states on a bulk that's otherwise boring, and that when we extend that picture from global symmetries to other kinds of symmetries, dipole symmetries, subsystem symmetries, interplay between U1 symmetry and lattice symmetries, that we get new kinds of topological response theories that can bring us new insight about what can happen in real materials. And so let me end there and I'll take questions.
Thanks. So are there any questions? I actually have a question about your last slide. So so here in this model that you described with this subsystem symmetry in the X and Y leaves, you have somehow an underlying square lattice structure, right?
Yeah, absolutely.
The symmetry group is some dihedral group of symmetries of a square. Is there a systematic way to like a top-down way to build topological response theories, keeping in mind that the microscopic theory might have certain lattice structures, say, triangular lattice, or starting from a space group, can one build just systematically gauge response here?
Yeah, good. So the way, so this is discussed. I had some work with Yiji and Trithep and Shivaji Sandhi, which I think we called it something like higher rank BF theories or higher, I can't remember exactly the title. So we discussed that a bit there. And there's also Nadi Seiberg and Shuheng Shao have a series of papers where they, kind of flesh this out. But so the basic, and they kind of started from like scalar field transformations and then went to gauge theories, and we started from gauge theories. But the basic idea is this. So I start with a lattice, which has a crystal symmetry group. Okay. And then I say, so let me talk about gauge fields. Okay. So now I say, let's suppose that I have gauge fields that are not vector gauge fields. Okay. So they transform in some, and the kind of the minimal thing is they transform in some tensor representation of the symmetry group. Okay. And then I can look at different tensor representations. And, so sometimes I could even have more than one kind of gauge field transforming in these different tensor representations. And, for each tensor representation, that's going to give me some number of gauge fields. Okay. And once you have those gauge fields, and the nature of the tensor representation, like basically, okay, if you assume that your gauge parameter is a scalar, and that's not necessary, so there's a different class of theories which I didn't talk about here, where you assume your gauge parameter is actually a vector parameter. Okay, but the simplest case, let's assume the gauge parameter is a scalar, and so then the gauge transformations of your gauge field are just completely fixed by this choice of representation, because AXY has to transform in a certain way under these crystal representations, and that is actually going to fix which derivatives can go into these gauge transformations of alpha, which is a scalar under rotation. And you can generalize that to vectors, in the obvious way, with the caveat that you now have to pick, what your vector gauge parameter, what happens to it under these rotations. Okay, you have to account for that. And so now, you have these gauge fields, you have these gauge transformations, and then you can just ask, okay, is there, can I write down Chern-Simons like terms, for example, right? Can I, like I have, once you have the gauge transformations, you can write down E and B, right? And sometimes there's one B field, sometimes there's two B fields, like depends on what representation these gauge fields transform in, and then you can work with E and B and so on, and ask, can I write down sort of topological type terms? And those are the ones that we would typically expect to give us SPT phases, or maybe more exotic things if we actually gauge them.
I see. And they're usually kind of mixed Chern-Simons, BF theory kind of topological terms, or do you also have something like the twist, like Dicraft twist? Right.
Okay, so That depends. So that depends on the rotation group that you keep. So if I suppose that I'm interested in 3 dimensions specifically, okay. So in 2 dimensions, these theories, these higher rank gauge theories, you know, kind of like electromagnetism in 1 dimension, like there is no magnetic field. And so, you know, it's kind of boring. So 2 dimensions is like that for these guys. And so, you know, the first place that you might think to look for exciting stuff is in 3 dimensions. Okay. And then, so basically, if you want to have a self-Chern-Simons term and have a fully gapped spectrum, the way that I know how to do that, I'm not saying this is the only way, but you know, the way that I know how to do that with these scalar charge theories is I have to pick a symmetry group such that there's only one component of the magnetic field. Okay. And so there is like, so we do have an example of that, where you basically, you start with a cubic lattice and you squash it so that you only get these like 3-fold rotations. Okay. And then it turns out that you can get a theory with only a single component of the magnetic field. And in that theory, you can write down a Chern-Simons like term. And it's a very interesting theory because, you know, it sort of looks like, I mean, it has this kind of chiral anomaly on the boundary. And yet you can also show that you can write down like a commuting protector lattice model that realizes it. So clearly there's no, you know, you can kind of gap out those boundaries. There's no gravitational anomaly. But so you can do that, but certainly it's much easier to write down these mutual Chern-Simons theories. I would say there's more of them basically, because you get to put on more constraints.
I see. Thanks.
Yeah, so I have a question. Well, first, thanks for the talk. It was pretty interesting. So I was wondering if you have any idea if you could have like higher form subsystem symmetries protecting some SPT. Like naively, I can imagine like the boundary could be some fracton order. Maybe this would have to be like a 4+1 DSPT, but I don't know. Have you thought about that at all?
Yeah. So I do have a paper with Shuheng and Hotat and Trithep and Pranay, where I talked about a couple of things today, but we did lay out a bunch of them, and indeed there are analogs of, you know, higher form anomalies for this, you know, which pretty much like you would expect. So yeah, we do discuss that a little bit, although I think it's, you know, do I have any kind of systematic understanding of that? You know, no, I mean, we have an example or two.
Okay, in your examples, like what are the boundary models like?
Yeah, so so you can realize, I mean, so when you say what are they like, what are you?
Oh, I guess so. You say
saying
you have some
specifically?
examples. So like, I guess I wonder, like maybe you have like an example where you have like an XQ model on the boundary or something.
Right. No,
And some,
indeed.
like,
Yeah.
Oh.
That's right. Yeah.
Okay, so you do have like,
you
you have
think about-
X cube or something.
Yeah.
Okay, cool. Thanks.
I am wondering if so usually for SPTs, you can have a boundary that is symmetric and gapless, or you can spontaneously break the symmetry. So if you spontaneously break the symmetry here, then would you have like an infinite number of Goldstone modes?
Yeah. So I'm trying to think, like in the actually, good. So I haven't thought very much about the symmetry broken boundaries and so I think in the but so typically so let's start, with the SPT case where I think this is kind of clear. Like, so when I take an ordinary SPT, right, and I have this anomaly inflow between, the bulk and the boundary, and it's associated with a global symmetry. And so, for example, some of these things are protected by U1 and charge conservation. And so what happens when you break the symmetry, then, the symmetry is broken, and so there's no goldstone. And what typically happens is you just gap the edge. And so, in the cases where I know how to write down explicit lattice models for these things, which you often can do, then, so certainly in those cases, it seems like that's true too, right? So, the simplest case, these corner modes, the Kramer's degeneracy, if you break, for example, time reversal symmetry, you just lift the degeneracy. Or if you break the U1 conservation. And for this kind of axial anomaly thing, But
that's explicitly breaking the symmetry, right?
Oh, you're asking like if you had interactions?
Yeah, spontaneously breaking the symmetry.
I see.
Yeah, I just thought because you have an infinite number of generators for this subsystem
Yeah,
symmetry,
so certainly if I take just a 2D system with this subsystem symmetry, that is true, right? That, I put it on a lattice and I get some, I get a goldstone mode for each direction, sorry, for each symmetry that's spontaneously broken. But yeah, the ones on the surfaces, right? You would think, but in those cases, I don't.
May I make a comment? I mean,
Yeah.
one would also revisit Mermin-Wagner theorem for subsystem symmetries, and that
Mhm.
may change the answer depending on the dimension.
Yeah,
Maybe it's
for sure.
possible that these are, that there's something, not to mean that there could still be massless modes without breaking the symmetry.
I see, because you're saying these are like 1D kind of continuous symmetries, so maybe you can't.
That's right. So probably it's very different now. So I would suspect that in two spatial dimensions, you still cannot spontaneously break some of these symmetries, and so one has to keep that in mind as well.
Okay, I guess that's interesting.
I don't know.
Yeah,
and it's just a guess. I don't know.
Yeah, no, I agree.
Okay, yeah, thank you.
Yeah.
You can probably thank Fiona and then stop the recording now.